Looking up and admiring the night sky, observing the vastness of the universe emblazoned upon us in a blanket of stars. This simple but deeply enriching practice connects us directly to our ancestors. Just imagine, in the not-too-distant past, our ancestors experienced this same wonder without the barriers of light pollution that today keep us from this experience in large urban centers. Entire civilizations were shaped under this starry sky, with many dedicating their lives to understanding celestial patterns. But have you ever wondered how this fascination with the night sky has influenced human and scientific development throughout history? Let's take this journey through time together, starting with ancient Greece, whose contributions are fundamental not only for the detailed records they left us, but also for the lasting impact of their ideas on modern science, influencing great minds such as Newton and Kepler. However, it is crucial to remember that Greece did not have the exclusive right to study the stars. From incredibly accurate calendars in the Americas to meticulous observations in China and the Middle East, astronomy is a truly global and ancient field. Imagine observing the sun, moon, stars, and comets at the same time as Ptolemy, with his geocentric theories, or Copernicus, proposing a heliocentric vision that challenged centuries of knowledge, or Galileo, with his telescope, revealing worlds never before imagined, challenging the vision of a perfect and unchanging cosmos. Kepler, in turn, offered a new model for the movement of the planets, with laws that still form the basis of astronomy today. And then we have Newton, whose theory of universal gravitation united the heavens and the earth under common physical laws, a true revolution in scientific thought. First, we need to talk about Johannes Kepler, the guy who looked at the sky and thought, "There's more than just circles here." Yes, because before him, it was believed that the planets danced across the sky in perfect circles, as if they were at a galactic ball hosted by the sun. But Kepler saw much further. So what is this ellipse he talked about so much? Imagine trying to draw a circle, but instead of a ruler, you use a string with 2 nails in it. As you draw, you realize that you've created a shape that looks more like an egg than a soccer. This egg is our ellipse, and the 2 nails are the famous foci. And then, the sun, which loves to be the center of attention, is actually in one of these foci, not right in the middle. Now think about Kepler's first law. All the planets in our solar system are basically in an elliptical obstacle course around the sun. And while it may seem that they like to live on the edge, their orbits are actually surprisingly close to perfect circles. But make no mistake, no one here is taking a walk in the park. This changes everything about how we understand planetary motion. Moving on to the second law, imagine you're playing one of those connect-the-dots games, but with the sun and a planet. If you draw a line between them over time, that line will sweep over equal areas at equal intervals. This means that when a planet is closer to the sun, it basically hits the turbo button and travels faster. And when it's further away, it slows down to enjoy the view. And last but definitely not least, Kepler's third law gives us a formula worthy of putting on a t-shirt. It tells us that the square of the time it takes a planet to make one complete revolution around the sun is proportional to the cube of the planet's average distance from the sun. Sound complicated? Well, it's just a fancy way of saying that the further you are from the sun, the longer it takes to go around it. Mercury, for example, is the agile student of the class, completing its lap in just 88 days, while we on Earth take a good old 365 days, plus a quarter, don't forget leap years. Just imagine a comet passing through the sky, observed by the giants of astronomy, Ptolemy, Copernicus, and Kepler. And then it shows up again in 1682, just before Isaac Newton shook the structures of physics with his book Principia. Newton was there, possibly contemplating an apple, or perhaps having a snack, and began to wonder, why do things fall? And not just here on Earth, but how do the planets up there keep moving? He was faced with 2 puzzles, one celestial, trying to decipher the movement of the planets following the clues left by Kepler, and the other very earthly about why a simple apple insists on finding the ground. Now, imagine the scene, objects thrown, cannonballs fired, And then Newton has that snap. He realizes that both the falling apple and the movement of the planets are governed by the same force, gravity. Yes, this force that keeps you stuck to the ground is now, believe it or not, the same force that keeps the planets around the sun. Here comes the part that makes you rethink your whole existence. This force of gravity not only pulls the apple towards the Earth, but also the Earth, with all its size, gives the apple a little tug back. Fair enough, right? But it gets even better. The same logic applies to the sun and the planets. They are in an eternal free fall around the sun, in a cosmic dance that never ends. And the astronauts, floating out there in space, thinking they've escaped gravity? Not at all. They are actually falling around the Earth all the time, in such a perfect free fall that they never land. Gravity depends on the mass of the objects and the distance between them. The bigger they are and the closer they are, the stronger the attraction. And this force decreases with the square of the distance. Basically, if you double the distance, the force of gravity becomes 4 times weaker. Let's take a look at something everyone knows, a falling apple. Simple, right? But here's the magic. The same formula that explains why that apple hits the ground is the one that keeps the moon spinning around the Earth and the Earth around the sun. And why does this matter to you? Because it shows that we are not disconnected from the rest of the universe. We're all under the same cosmic rules, participating in a universal choreography, whether we're throwing a soccer or simply sitting back to admire the sunset. But why doesn't the moon get tired of this dance and fall to Earth? Because it has the energy to keep the right distance. It's a delicate balance between the energy that wants to launch it out into space and the gravity that wants to bring it back. And that's what keeps all the planets in their orbits, in the perfect harmony that makes the universe work. Now, looking at all this, can you believe that we are all connected by these invisible forces? From a simple apple falling from a tree to the immense complexity of the planet's movements, it's all part of a great cosmic ballet. And to think it all started with someone wondering why things fall. So the next time you look up at the sky, remember, there's a lot more going on up there than we can see. And it was all unraveled by curious minds who weren't afraid to ask, why? So, are you ready to discover the next great mystery of the universe? Maybe you'll find the answers we're looking for. See you on your next adventure for knowledge, and until then, keep looking at the stars.